Assalamualaikum and very good morning to all of you. Welcome back to our class. Today we still in topic number 4, which is the seismic design for reinforced concrete building. In part 4, we will discuss about the behavior factor. Okay, before we start with the behavior factor, let me recall back your memory about our lessons in topic 2, which is the design response spectrum. Okay, when we use this equation, which is equation 3.13 to 3.16, we will see a parameter or a variable here, which is known as alpha G, S, T, TB, TC, and TD. And also we can see the Q here. Actually, what is Q? Q is the behavior factor. And let me ask you one question. What will happen to the SDT1, the spectral accelerations, if the Q is reduced? What will happen to this one?
Increase.
Okay, this one will increase. And then as a consequence, what will happen for base shear force?
Increase.
Okay, it also will increase. What will happen to the Fi, which is the story force?
Increase.
Okay, good. This one is also increased. What will happen to the bending moment?
Bending moment. Increase.
Okay, good. With bending moment will increase. With higher bending moment, what will happen to the area of steel required? Because we are talking about the reinforced concrete, we need the steel inside the concrete as reinforcement. So what will happen to the AS required if we have high
Increase.
bending moment? It will increase, right? Okay. And then what will happen to the AS provided? We should provide.
Increase.
Okay, we should provide more than required. So if the AS provided is increased, means the amount of steel is increased. Okay, we need more amount of steel for lower behavior factor. Okay, what will happen to the cost if we need higher amount of steel?
Increase juga.
Okay, cost also will increase. Okay, good. So this is to recall back. Okay, we have three class of ductility, which is ductility class low, and then ductility class medium, and ductility class high. Depend on the seismicity region. Okay. Okay. This is why. That's why we need the behavior factor. I can recall back your memory about the requirement of ductility design. Okay, if we design for ductility class low, we need to design for very high forces, and the cost will be very high. However, if we design for ductility class, a higher class of ductility, either medium or high, we will design for lower forces and we will design with lower cost. So behavior factor is introduced for this purpose, which is a factor used for design purposes to reduce the forces obtained from a linear analysis in order to account for non-linear response of a structure associated with the material, structural systems, and the design procedures. Because in earthquake engineering, it is not economically feasible to design structures to respond elastically due to earthquake ground motions. That give me example. We have two types of structure, namely as structure A and structure B. However, structure A we design for elastic response spectrum, where the response will remain elastic. Okay, and design structure B we design for design response spectrum where we reduce the forces, okay, reduce the elastic response spectrum by a factor. Okay, let's say we design the structure A, we designed for the base shear force of 2000, okay, to make sure that it will acting linearly, okay. And the structure B, we reduce the forces, we design for 500 kilonewton, which is 4 times lower than structure B, structure A. And the structure B will acting inelastically. Okay, after the certain point, it will yield and it will behave inelastically. So the factor noun, the ratio known as behavior factor. Okay, because if we design as a result, if we design the structure A for very high forces, we will have a very high size of sections. Okay, let's say column, very high size of column, very high amount of steel reinforcement, very big diameter, maybe like this one. Compared to the structure B, because we design for lower forces, so we can reduce the size of column and we can reduce the amount of steel reinforcement here. So we can reduce the cost. Okay. Okay, for based on this table, for ductility class low, this is the value of behavior factor, and this is the range for ductility class medium, and this one is for ductility class high. For RC moment resisting frame, in Malaysia, we only consider ductility class low and ductility class medium. Okay, you can recall back our last lesson about the seismicity cases. Okay, based on the seismicity cases, then we determine the class of ductility to be considered, and then we can determine the value of behavior factor to be applied in design. Okay, so this one, as according to Eurocode 8, clause 5.3, for ductility class low, the behavior factor up to 1.5 may be used in deriving the seismic action. So for DCL, that the behavior factor is equal to 1.5 only. Okay, and how about the ductility class medium and high? We refer to this clause of Eurocode 8, and based on these equations, the behavior factor is equal to basic value of behavior factor times the KW, which is the factor reflecting the prevailing failure mode in structural system with walls. Okay, but it must be greater than 1.5. Okay, this table 5.1 in Eurocode 8. This is for the structural system, either the frame system, dual system, or couple wall systems. This is the basic value of the factor. The Q naught is, let's say for DCM of frame system, the Q naught is equal to 3.0 times alpha U divided by alpha 1. For DCH is 4.5 times alpha U divided by alpha 1. This is the value proposed by the Eurocode 8 for different type of structural systems. Okay, and this is the value of alpha U divided by alpha 1 as proposed by the Eurocode 8. Okay, for buildings which are regular in plans, the following approximate values may be used. Okay, regular in plans means from the bottom to the top part of the building, the floor plan is similar. Okay, that's what they mean by the regular in plan. Okay, frames. Okay, part A is the frames or frame equivalent dual system. Alpha U divided by alpha I is equal to 1.1 for one-story building. For multi-story 1-bay frames, the value is equal to 1.2. For multi-story multi-bay frames or frame equivalent dual structures, the value of alpha u divided by alpha 1 is equal to 1.3. And this is the corresponding value for the wall or wall equivalent dual systems. And this one is the value of kW, which is the equal to 1.0 for frame and frame equivalent dual system, which is for this category of structure. And then for category B, we have to derive based on this equation, okay, the value of kW. Okay, we have, okay, recall back, this is A is frame or frame equivalent dual system, and B is the wall or wall equivalent dual system. Okay, let's take a look on the frame equivalent dual system. Okay, this one, let's say this is frame system. This is moment resisting frame system. And then when we talk about dual system means we might have shear wall here. Okay, this is wall. However, the wall only cover the wall cover less than 50% of the base shear force. Okay, let's say this is the base shear force. Wall, okay, the frame resist 50% to 60% or 65% of FB. Means the majority of the forces is resisted by the frame system, by the wall, by the column, and by the beam. Okay, where this wall only covered around 35%. Okay, 35% to 50%. Okay, how about the wall equivalent dual system? Okay, let's say this is a frame. This is a frame system, and dual systems means, let's say we have a very large area of shear wall here. Let's say here, this is a shear wall. And then this is your FB, you see. And the wall, okay, the red color, the wall resists 50% to 65% of base shear force. Okay, and the frame system, the column and the beam only resist 35% to 50% of the FB. This is the dual system, either frame equivalent or wall equivalent. Okay, let's take a look on this one of how we derive the value of alpha u divided by alpha 1. Okay, for this one, for this case, the frame or frame equivalent dual systems means this one is frame resist 50% to 65% of FB. And then for one-story buildings, the value of alpha u divided by alpha 1 is 1.1. Okay, here, this is an example of one-story building. So the Q naught, Q is equal to, sorry, I better do it here. Q is equal to Q naught times KW. So the Q naught is equal to, for DCM here, this is the DCM, is equal to 3.0 multiplied by alpha u divided by alpha I. And for one-story building, the value is equal to 1.1. Therefore, 3.3 times 1.1, the equal to what? 3.0. 3.0 times 1.1 equal to 3.3, right? Okay, this should be 3.3. And then for frame and frame equivalent dual system, the value of KW is equal to 1.0 So we make it here 3.3 times 1.0. So the Q is 3.3. Okay, that's how to derive the Q. And then you can go to the SDT1, blah, blah, equal to blah, 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 depend on the value of T1. Okay. So next, for multi-story one-bay frame, the value is, okay, let's say we stick with the DCM. Okay, and this is the multi-story one-bay frame. Maybe you can remember back, okay, during your school time. Okay, maybe this is the roof trusses, pitch roof, I mean. And then we might have a corridor here. Okay, this is multi-story. Okay, one story, 1, 2, 3, 4, 5, up to 6 story, but only one bay. Okay, this is one bay. We call from column to column, and we call it only one bay. This is why we call this system is multi-story and one bay frame. So, can you give me what is the value of Q naught? Q naught is equal to alpha U divided by 3.0 times alpha U divided by alpha I. So what is the value of alpha U divided by alpha I? Alpha 1, sorry. For this type of structure, multi-story one bay frame, what is the value?
1.2.
Okay, good. 1.2 here, this one, okay. So 1.2, so Q naught is equal to?
3.6.
Okay, 3.6. However, this is the Q naught. Okay, so we have to determine the KW. KW is still 1.0 because it's a frame equivalent dual system. So Q is equal to Q naught times KW equal to 3.6 times 1.0. So equal to 3.6. Okay. For wall, if the wall resists more than 50% of the FB, is under category of wall equivalent dual system. So we have to derive based on this one. Okay, this is for higher level of study, we can go through this one. For the undergraduate, so I only limit to frame or frame equivalent dual system. Okay, and then the multi-story and multi-bay frame. This is an example. Okay, multi-story and multi-bay frame. We have a total number of bay is equal to 1, 2, 3, 4 number of bay, and then number of story is 1, 2, 3, 4, 5, and 6. That's why it's called as multi-story and multi-bay frame. Let's say we have a shear wall here as a lift core. However, the shear wall only cover the wall cover 35% of FB, and then the frame will resist around 65% of base shear force. So the system is now as frames or frame equivalent, not wall equivalent, it's frame equivalent because the frame dominate the resisting system. So for this case, Q naught is equal to, if we change to DCM, okay, still stick with DCM, 3.0 multiplied by alpha U divided by alpha 1. What is the value of alpha U divided by alpha 1?
1.3.
Okay, good. This one, this under this category, multi-story, multi-bay frame. Okay, or frame equivalent dual structures. This one, 1.3. Okay, 1.3. So equal by 3. Good, 3.9. And Q equal to Q naught times KW equal to 3.9 multiplied by still 1.0 because it's still frame equivalent dual system 1.0, so it's equal to 3.9. Okay, that's how to derive the behavior factor. Okay, that's only for DCM. You can practice about the DCH, what happened. DCH, okay, in your opinion, the value of behavior factor for DCH is higher or lower than DCM?
Higher.
Yes, good, higher. Huh? So DCH, okay, this one, the Q factor for the DCL, ductility class low, ductility class medium, and ductility class high, the value will be higher, right? Okay. Okay, so it should be like this one. Huh? This one is DCH, and this is the SL. Okay, higher factor. The value will be higher. So as we mentioned before, SGT1 will be lower. The base shear force also will be lower. The story force also will be lower. The bending moment lower. What happened to the AS required? Also lower, and AS provided also lower, so we can reduce the cost. Okay, this is the concept of a difference of ductility design. However, for DCM and DCH, there will be special requirement. I mean, special requirement uh, for checking. Okay, we will take a look. We will learn about this one in our next lesson. Okay, that's all. Thank you very much for your cooperations. Thank you very much for your time. Get ready for our next lesson, which is the seismic design of beam and column with ductility class medium. Okay, that's all. Thank you so much. Assalamualaikum. Bye-bye.